Hello and welcome to Unit 8. In Unit 8, we're going to continue our investigations of the concepts of work and energy. In Part 1 here, we're going to work on path, or sometimes they're known as line integrals. So what is a path or line integral? It is an integral that follows a particular route through space from point A to B. So, for example, I could take a route from A up to B that goes like this, or I could take one that goes like this, or I could take one that goes along the diagonal. 3 possible routes from A to B. To illustrate path integrals, I'm going to do three sets of integrals, if you will, following the 3 paths that I just showed for 3 different possible forces. So the first force is just the force due to gravity. And we're going to look, as I said, at the 3 different paths from A up to O, then across to B, A across to Q, then up to B, and then going directly from A to B along the diagonal. First thing we're going to do is we're going to write down what this force is. So the force in this case is the force due to gravity. And it will have a value of mg and will be directed in the negative j hat direction. If I plug in 3 kilograms and 9.8 meters per second squared, that gives me a force with a magnitude of negative 29.4 newtons directed in the j hat direction. To begin with, let's consider the path A to O to B. So if I look at the work, it's going to be the integral from A to B of f dot dr. This is going to be broken up into 2 pieces. The first piece is going to be from A to O, and as I go from A to O, dr will be dy. So this will be negative 29.4 newtons in the j hat direction, dotted with dy in the j hat direction. And the second piece will go from O to B, in which case dr will be a dx. So that would be negative 29.4 newtons j hat dot dx I hat. And you can see that this second integral automatically is going to go to 0 because j dot I is 0. Looking at the integral from A to O, that would become negative 29.4 newtons times the integral from y equals 4 to y equals 20 dy. The integral of just dy is y, so this becomes 29.4 newtons times y evaluated from 4 to 20, and I need some units here, so we're going to add the units on my limits. Plugging in the units and multiplying everything out, I get negative 474.4 joules. Now let's redo this exact same integral, but instead follow the path from A to Q to B. When I go from A to Q to B, I start off the same way. Again, I'm going to break into 2 pieces for my path. I'm going to go from A to Q first, and that will be my force, negative 29.4 newtons j hat, dotted with dx I hat. And then I'm going to go from Q to B, and if you look, the first integral is 0 again because j dot I is 0. And the second integral is going to work out to be the exact same integral we had for the AOB path. So this will also work out to be negative 470.4 joules. Lastly, let's go along the diagonal. Along the diagonal, dr has 2 pieces. So my integral will become the integral from a to b of negative 29.4 newtons j hat dot dx I hat plus dy j hat. Again, I dot j goes to 0, or j dot I goes to 0 in this case, leaving me with the integral of negative 29.4 newtons times the integral from 4 to 20 dy, which is again the same integral I've already done, and so this will equal negative 470.4 joules. Now you're probably thinking, well, path integrals don't seem so bad. Okay, I started off with a special case. Okay. Let's go look at a slightly different case where again we have a constant force in magnitude, but it's the force of friction. So along each part of our path, it's going to change direction. Okay. We're again going to start with the integral of AOB. So I'm going to have the integral of f dot dr, and that will again be two pieces, the integral from a to o plus the integral from o to b. As I go from a to o, my force will be negative 16 newtons j hat. Remember, it's going to point opposite the direction of motion. Since our motion is in the positive y direction, the friction will point opposite that. dr in this case will be dy j hat. And from O to B, the force will be negative 16 newtons I hat dot dx I hat. Okay, so that leaves me with negative 16 newtons times the integral from 4 to 20 dy plus the integral from 1 to 10 dx. I could pull the negative 16 newtons out because it was in both integrals. It's a constant in both integrals. Doing this integral, the integral of dy just results in y. The integral of dx results in x. So I'm going to end up with negative 16 newtons times y evaluated from 4 to 20 meters plus the integral of x evaluated from 1 to 10 meters. Putting in my limits and adding everything up, that works out to be negative 400 joules. Next, let's go look at AQB. AQB is going to go very similar to AOB. So again, integral of f dot dr. The first thing I'm going to do is I'm going to go from A to Q, that is horizontal. So my force will be negative 16 newtons I hat dot dx in the I hat direction, plus the integral from Q to B of negative 16 newtons j hat dot dy j hat. These are the exact same integrals that we just did. And so I'm going to get the exact same number out, negative 400 joules. Now let's consider going along the line from A to B. Okay. Well, along the line from A to B, my force is going to point in the negative of that direction. And to find that, I need to look at my triangle a little bit. Oh, that is the wrong line. Let's try again. I have a triangle. I'm going to go back 2 slides and show you what triangle I'm meaning. It is this one right here, where here's my hypotenuse. If you look, this side has a length of 9. This side has a length 16. That makes this angle 60.6 degrees. You can find that with an inverse tangent. Okay. Knowing that, I can now write my force as equaling negative 16 newtons times the cosine of 60.6 degrees in the I-hat direction plus the sine of 60.6 degrees in the j-hat direction. Okay. This whole piece with the negative sign gives me the direction of that vector. It doesn't affect the magnitude because remember, cosine squared plus sine squared equals 1. Now when I take the integral from a to b of f dot dr, I get the integral again from a there we go, from a to b of negative 16 newtons times the cosine of 60.6 I hat plus the sine of 60.6 j hat dotted with dx I hat plus dy j hat. That's my dr in this case. Well, this separates into two pieces, one in the x direction and one in the y direction. The x integral looks like the integral from 1 to 10 of negative 16 newtons cosine of 60.6 dx. And I need to add to that the y integral from 4 to 20 of negative 16 newtons sine of 60.6 dy. If you look, nothing in the argument of either integral depends on the dx or dy. So I can pull that out, which lands me at this statement. And if I plug in numbers, I get 293.7 joules. So we see that while AOB and AQB gave us the same values for this integral, if I go directly from A to B, it gives me something different, which is not surprising because I am covering less distance along the hypotenuse, and therefore the force of friction is going to have less chance of doing work. That's why the integral from A to B is less than the integral when you go from A to O to B or A to Q to B. Okay. For the last example, I have a force that depends on X and Y. And I again want to do the same integral, AOB, AQB, and AB. For AOB, I'm going to do the integral from A to B of f dot dr. And this will again break up into two pieces. The first piece, dr, is in the y direction, so the only piece that's going to matter is the 2xy portion of the dot product. And then if I go from O to B, dr is going to be di, so I'm going to go from 1 to 10 of 16x dx. Okay. For the first integral, along the path from A to O, x is constant at equal 1. So we can plug that in. So I end up with 2 times x equals 1 times the integral from 4 to 20 of y dy. And I dropped an x when I wrote this here, so I'm going to put it back in. Integral of just y is going to be y squared over 2, so I'm going to have 2 times y squared over 2, evaluated from 4 to 20. Integral of x dx is going to be x squared over 2, evaluated from 1 to 10. Plugging in the limits and assuming all the units work out, this ends up at 1,176 joules. Now let's look at a QB. So again, integral from a to b of f dot dr. Again, I'm going to break it up into two pieces. The integral from a to q dr will only be in the x direction. So I can write this as the integral from a to q of 16x dx. And then I'm going to write it as the integral from q to b. dr in this integral is only going to be in the y direction. So that's going to equal 2xy dy. For this integral, x is again going to be constant, but if we look, along q to b, x is a constant at 10. So I'm going to have the integral from 1 to 10 of 16x dx plus the integral of 4 to 20 of 2 times x fixed at 10 y dy. Again, doing the integrals. Plugging in the limits and adding everything up gives me 4,630 joules. So unlike the first two examples, where I had the constant force, that resulted in the integrals from a to O to B and the a to Q to B to be the same. For this example, where my force depends on x and y, I have lost that symmetry, and AOB does not equal AQB. Now let's go look at the direct path from A to B. For this one, I have to be a little bit careful. Okay. So this will equal the integral from A to B of 16x I hat plus 2xy j hat, dotted with my dr, which is going to be dx I hat plus dy j hat. Okay, this again breaks into two pieces. I end up with an integral from 1 to 10 of 16x dx plus the integral from 4 to 20 of 2xy dy. Now, unlike the previous two paths, where I could make x constant for this second integral, I can't do that here. I need to know how the value of x changes as y changes. Well, luckily for us, we're going along a linear path from A to B. I can use the rise over run to find the slope of this line, and then I can use a point on the line to find the y-intercept. That results in a slope-intercept form for the line of 16/9 x plus 20/9. In order to use this, I need to solve for x. So x will equal 9/16 times y minus 5/4. I'm going to leave that as an exercise for you. One, to find the equation for the line if you really want to find it and verify it, and also to rearrange it to solve for x. I can now take this relationship between x and y and plug that into, oh, that is not an integral. I don't know where that came from. Try again. Integral from 4 to 20 of 2 times 9/16y minus 5/4 times y dy. Okay, so this integral we've done. This is 16x squared over 2 evaluated from 1 to 10. I have two integrals I need to do here. The first is 2 times 9/16y times y. So that works out to be the integral of 9/8 y squared, or 9/8 y cubed over 3 evaluated from 4 to 20. The next one I need to do is 2 times -5/4 times y. That works out to be -5/2 times y squared over 2, again evaluated from y = 4 to y = 20. Plugging in the limits of integration, this results in the total work done being 3,288 joules. And we see for this force, we get a different value for the work done for all three paths we could take. This concludes this part.